In this section, we're going to be looking at theoretical probability, and we already talked about empirical probability, which was where we used an experiment and repeated an experiment over and over to try and find a probability of an event. What we're going to do now is move on to theoretical probabilities, which is where we're basing our probability calculations on theory rather than experiments. And so the first step in calculating a theoretical probability is to count the total number of possible outcomes. That ends up being probably the most challenging part as you get to more complex probabilities. Step 2 is to consider all possible outcomes and count the number of ways the event of interest can occur. And then step 3 is to determine the probability of A. We write that P of A, so A is in parentheses, using the formula. Probability of A is the number of ways A can occur out of the total number of possible outcomes. So if we go back to our single die experiment, by calculating all possible outcomes that can result from the experiment of rolling a fair die, we know that the theoretical probability of rolling a 5 can be calculated by taking the number of ways to roll a 5, which there's only one way to roll a 5, out of the total number of possible outcomes. Well, when we roll a 6-sided die, there are 6 possible outcomes, and so that theoretical probability is 1/6. And so just as a reminder here, I wrote that the empirical probability and the theoretical probability are not always going to be equal, but if the theoretical probability is correct, then as the number of trials increases, so we're repeating our experiment over and over and over, what's going to happen is that empirical probability is going to start getting closer to the theoretical probability. And we saw that happening in the last video and talked about that being the law of large numbers. So what we're going to do next here is we're going to look at calculating some basic probabilities. And so the first example we're going to look at, we are asked to find the probability of drawing a queen from a standard deck of cards. So the probability of a queen. And the probability of drawing a queen is going to be the number of ways to draw a queen. Out of the total number of possible cards that can be drawn. And so just in case you're not familiar with a deck of cards, I just wanted to show you real quickly. So a deck of cards has 4 different suits. So you have your clubs, your spades, your hearts, and your diamonds. The hearts and diamonds are red. The clubs and spades are black. There are 13 cards of each of those suits, and those are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then jack, queen, and king. The jacks, queens, and kings represent another group that we call the face cards. Okay, so that's what a deck of cards looks like. If we're trying to find the probability of drawing a queen, hopefully you can see both here. You will notice that the number of ways to draw a queen, well, there are 1, 2, 3, 4 queens in the deck out of 52 cards total. So that probability would be 4 out of 52. You can write that as a fraction. You could write it as a reduced fraction. You could write it as a decimal if you wanted to as well. Okay. Next one, we're supposed to find the probability of meeting someone with a phone number that ends in a 1 or a 2. So I'm just going to put probability 1 or a 2. So if we're looking at the possible ending numbers of a phone number, the choices are 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there are 10 possible endings to a phone number. How many of those are 1 or a 2? Well, two of them, right? Either a 1 or a 2. And so we would get 2/10 or 1/5 as that probability. Next basic theoretical probability is asking us to find the probability that a randomly selected person has a birthday in June. So the probability of a birthday in June is going to be the number of ways to have a birthday in June over the total number of possible birthdays. Well, if we want to know how many possible birthdays there are, well, there's 365 of them, right? The number of days in a year. So your birthday could be any one of those 365 days. How many of those are in June? Well, there are 30 days in June, and so 30 out of 365. Which, if we wanted to convert that to a reduced fraction, we would just hit enter here and then do math, arrow fraction, enter, and the reduced fraction there is 6 out of 73. Or you could write it as a decimal. And then this next one here, we're asked to find the probability that a randomly selected person does not have a birthday in June. And the reason I introduced this one is because these two events are what we call complementary events, or complements of one another, because they are the probability of an event and then the probability of not that event. And so the way we can find a complement probability is take 1 minus the probability of the event itself. So if I want the probability that someone was not born in June, I can just take 1 minus the probability that they were born in June. So if I wanted to, the other way I could do this is I could find the probability that they were born in January, February, March, April, May, July, August, September, October, November, and December. But that's a long process, and so it's going to be faster just to say, well, everything else, right? Either they were born in June or they weren't. So everything else is going to be part of not June. So we need 1 minus 30 out of 365. And we can change that using that same technique, doing math, arrow fraction, and hitting enter. And so that's 67 out of 73. And that should make sense. When we looked at the probability that someone was born in June was 6 out of 73. If we take those 6 away from 73, we're left with 67 that were not born in June. Okay, so it's not a surprise that those two probabilities sum to 1, because we were forcing that to happen, right? Either the event occurs or it does not occur. Those are the only possible outcomes. All right, so the last thing here that we're going to cover in this video is just some of the basic properties of probability. And so first thing is that the probability of an event is written P and then in parentheses that event. And I'll usually just use a shorthand word or notation, or sometimes even a letter to represent that event. Second, the probability of any event has to be between 0 and 1. That is inclusive, meaning you can have a probability of 0 and you can have a probability of 1. But anything bigger than 1 or less than 0 can't exist. If the probability of an event is 0, we call that event an impossible event. And if the probability of an event is 1, we call that event a certain event. So an impossible event can't happen because its probability is 0, and a certain event has to happen. Its probability is 1. And then the last property here is that the probability of A not occurring is 1 minus the probability of A occurring. And so that was what we just did an example of and called that the complement. And so a probability of an event A plus the probability of the complement not A has to sum to 1, right? So if I look at the probability that something does happen plus the probability that it doesn't happen, then that sum has to be 1, and rearranging that is where we got this formula. Okay, so those are our basic introduction to theoretical probability.